Welcome to the fifth part of signal analysis basics. Today we're going to be discussing how to put signals into a computer. Well, first of all, let's start talking about the things that computers can and cannot do. Computers are generally digital. Computers are digital systems, so they deal with things that are discrete rather than continuous, whereas real life signals are continuous. Many people like to say analog, but analog is not actually correct. Analog is a word that has existed for some time and has now become synonymous with continuous signals. But an analog signal is really a signal that is analogous to a certain idea. But in this case, we'll be talking about signals that you might see in the real world, like the signal response of somebody singing as continuous, and signals that you would see on a computer, for example, a set of numbers that describe what a signal looks like when broken into specific bits of data as discrete. So, as you might expect, the first thing that we do is take a signal that's from the real world and break it up into a number of points. And we do that by multiplying it with an impulse train. And what we get out is something that looks like this. So we get a number of vectors that are placed where the impulse train is set, and each of the vectors' magnitudes are the magnitude of the actual the amplitude of the signal. So that works really well to put into a computer. But what happens when you put stuff like that into a computer and you try and bring it back is you get weird signals. Let me change that color. You get weird signals that look like this. So that is somewhat close to what we had back up there, but it is nothing like it at all. What we would like to do is to get an even smoother graph by increasing the number of points at which we sample. And if we increase the number of points to infinity, what we'll get is a continuous signal, but we don't have space in a computer to keep infinite points. So we have to deal with sitting at a certain number of points. Nowadays, doing 48,000, 22,000 is generally good enough. But a number of years ago, doing 48,000 rather was almost unthinkable with the amount of memory a computer had. You might have to leave a computer sitting for hours if you needed to get it done. So there were other tricks to dealing with it. One of those tricks is to take the signal into the frequency domain. So on the right over here, I have an equation of what the response would look like in the frequency domain. So x of f, cap x of x is equal to the integral of these things, the original signal multiplied by the transfer function, and then the Fourier transform of that, which, as we follow down here, comes out to x of t multiplied by the Fourier series, or multiplied by Fourier series over time, which ends up being looking something like this. It's just a bunch of data in the frequency domain. That's really useful, and that gets us a starting point in what we and how we can represent signals in a computer. But let's move forward and see how else we can make this how else we can try and recreate something like this up here from something like this. So moving forward, we will take if we take an original signal in real life, like this one over here to the top left, and we multiply it by an impulse train, then what we get out is impulses that show what the signal looks like broken up into bits. Now if we do the Fourier transforms to go to frequency, these are what those signals would look like in the frequency domain. X of t in time would come to x of f in frequency. Delta, an impulse train in time would become an impulse train in frequency that has a frequency period of n over t. No, n over t, or rather 1 over nt. There we go, 1 over nt, and that should be erased. I'm sorry about that. That should be 1 over nt. Yeah, and a height of t. So what this means is the closer you make this gap over here, the farther this gap is. And the farther this gap is, the closer this gap becomes. It's just a very interesting relationship. So the more n's there are within a certain period, I'm sorry, then I was wrong. It was n over t. The more n's there are within a certain period, the more points there are within a certain period, the further away the frequency points are. The farther away the frequency points are, the less the chance of overlapping in frequency happens, and the more data you can keep together in frequency. So that's why we need to have more points to sample. We get less overlap in frequency. So that gives us, in frequency, if we multiply the original times an impulse train that's derived from the time, we'll get something that looks like this, which is all our frequency components just repeated periodically in the frequency domain. So to go from frequency to time, once we found our frequency in the frequency domain, to go from frequency to time, we have a few ways that we can do it. One of them is to take the signal in time take the signal in frequency and equate it to let me see, did we have this on the last page? I'm sorry, please give me a second. We did not. Okay. Let me see whether I can describe what this is. This response over here is a frequency train over nt, so it repeats itself in the frequency domain, an impulse train in the frequency domain that's repeated every nt times. So we take that to find our time component. Our time component ends up being the coefficient of the frequency train. So we can say that x of nt is equal to the coefficient of the impulse train. That is equal to time. That is equal to the period times the inverse Fourier transform of our original signal to the left over here. And in this case, we're doing it when n is equal to 0, so that's why there's no n over t term. df. So we're just doing this shows us that we're doing the inverse Fourier transform. And if we take this over here, this signal is the forward Fourier transform of our signal. If you remember from the page before, we saw this. This is the forward Fourier transform right here of our impulse train. So let's go back. So let's take the forward Fourier transform of our let's represent that as the forward Fourier transform of our impulse. That's this over here, and we can put the e terms together and change the order of integration to do the forward Fourier transform of the inverse to find what it would look like in time. And as you can see, we get a delta function right here that brings us over here. And this delta function, integrating over delta function, just basically tells it to change whatever this is in the function to become this, so we end up with x of nt, as we expected. So if we want to go from if we want to find a signal in time, we take a signal, we do the forward Fourier transform of the signal. We take the signal, we multiply it with the input with an impulse train. We take the forward Fourier transform of that, and then we get the answer to that in frequency, sorry. And then we take the inverse Fourier transform of that, and we plot it back as we take the inverse Fourier transform of we take the inverse Fourier transform. I forgot to mention something very important. We take the inverse Fourier transform of this over here, the frequency domain component that has been made periodical, and we get the original signal back in time, as we expected over here. Thanks. I'll see you next time.